All right, so here's some review for you guys. The electromagnetic radiation, the wave model. There's a few questions on this, followed by a few questions on the quantum model. This would be material that I normally do for a diploma prep course that I usually do through Metro. So I'll just give you this information. I posted this as a blank copy on your Google Classroom. And let's go through a few of the concepts here. Once again, in case you haven't seen already, our exam will be on May 12th at 1 p.m. and that'll be on Smarter Mark. So please make sure you're there, you're available. Put some time aside. Give yourself about 2 hours from 1 o'clock to about 3 o'clock on May 12th will be your unit exam. If you have any questions, if you're working at that time or something else pops up, please make sure you're emailing me. But reminder, your unit exam is coming up not this week, but next week on Tuesday, May 12th at 1 p.m. All right, so the way you'll see this booklet set up is basically you'll have the outcomes on top followed by a question that usually matches that outcome or roughly matches. So let's talk about the outcomes. So the first one says we should be able to explain or describe how accelerated charged particles produce EMR. So just understanding that charged particles, when they accelerate, will produce EMR. This could be an example of electrons maybe vibrating up, vibrating down. This change of motion up and down would be releasing EMR because it's accelerating, decelerating, decelerating. And through that process, will definitely produce EMR. We also mentioned that whenever you have an electron and it's traveling in a circular path, technically it would have an inward acceleration. That inward acceleration is enough to make that electron produce some sort of EMR. All right, so that's the first one. Moving on. So it says compare and contrast constituents of the EMR spectrum based off their frequency and wavelength. So this is memorizing kind of where these things would fall. So here it says the ground penetrating EMR is classified as. So this is a whole section of the ground penetrating EMR. We're going from roughly, 4 or so to 15 times 10 to the negative 6. So if I had 5 to 15 times 10 to the negative 6, where would that fall? Would that be a radio waves, microwaves, infrared radiation, visible light, ultraviolet, gamma rays, x-rays? So remember, you should know the song. Remember that song that we went through in class and try to figure out roughly where these fall. So in this case here, is negative 6 smaller than 400 nanometers or is it larger than 700 nanometers? So I'll let you guys be the judge of that to try to figure that out. But remembering the spectrum and kind of where it fits along the side. So you may have to go back into your notes to kind of look at that, but that's something that you should know. The wavelengths roughly of everything else. The main one, the only numbers that you really need is visible lights, 700 to 400 nanometers. And just remember, anything smaller than that will be ultraviolet. Anything larger than that will be infrared, moving on to the microwaves and radio waves. All right, number 3 here, it says explain propagation of EMR in terms of perpendicular electric and magnetic fields with varying time as they travel away at the speed of light. So if you guys remember, we kind of tried to draw this in class where we had these particles, or the wave maybe had a vertical component. Okay, and then this wave is kind of moving in that direction. And then once again, kind of hard to draw, but I'll see if I can recreate this, a perpendicular field to that. And I know it's kind of hard. Hey, that's not too bad. Once again, remembering that this is now perpendicular 90 degrees from that surface. Hopefully you guys can kind of visualize that. And then it's moving away this direction at the speed of c. Remember, we kind of did that hand motion where we had one going up and down, the other one going side to side, but they're both moving away from us. You should use that idea to maybe solve these questions out. Once again, I'll see if I can post the solutions for these maybe a little bit later. All right, so next one is explain various methods of measuring for the speed of EMR. So I want you guys to go back and think about these positions. So we have an ancient method, which is Galileo's, using the little lanterns from the top of the hills. We had Romer, which used the idea of the Earth going around the sun. And we then once again looked at Jupiter and one of its moons as it went around. We said, well, if Earth was here compared to here, it took different amount of time for the light to reach us. And that different amount of time was because of the different distance that we were from Jupiter. And then from that, we were able to use that to find the speed of light. That was one way. That was, once again, Romer's method. And the other one was Michelson's method, which we'll take a look at next. So in the Michelson's method, we are using an 8-sided mirror. And in this case, light travels. It hits a certain section of the rotating mirror, travels a large distance, 30 kilometers in this case, and then back an additional 30 kilometers. So a total of 60 kilometers. Then hits the mirror. But remember, this whole thing was rotating so fast that this thing only had time to rotate one fractional of a rotation while light traveled 30 kilometers and back. So light traveled 60 kilometers, but yet this rotating mirror only rotated 1/8 of a total rotation. So maybe using this shorter equation, you guys can try this one out to maybe solve this one through. But hopefully that kind of reminds you of how to do these questions. Once again, if you have any questions a little bit later, make sure you're asking me on the Google chats. All right, the next one is the idea of refraction. So light will bend using Snell's law, either bend towards or away as it goes from different mediums. So we had mentioned before that as we're going from a light medium, let's say air, into something that's a little bit more dense, that the angle will bend towards the normal. Once again, the normal is perpendicular to the surface, and in this case, each one of these would have its own normal line. This is the n value, or normal, we call it. In this case, is asking for glass. The little shortcut that I mentioned probably in class, if you guys remember, is that you can actually jump from air straight to glass without going through the water situation. So if you're using Snell's law to solve this one through, you can say sine theta of air divided by sine theta of glass, and just use these ratios. And remember that index is always inverse of everything else. So in this case, we're using index of glass on top, and then the index of air down below. And in this case, we are trying to solve for theta g in this case here. Then the question above is just using a ratio as well, this time using 1.46. And then in this case, visible light in air, we need to remember that air always has the value of 1.00 for an index of refraction. All right, then we did some equations using Lenz's law. The Lenz equation, or the mirror equation. 1 over f is equal to 1 over do, distance of the object, plus 1 over di, the distance of the image. A few things you need to remember is that if you have a converging either lens or mirror, we're going to be using a positive focal point. And if it's diverging, we're always using a negative focal point. Another thing to remember is that if the image is virtual, it will have a positive HI, and it would also have a negative DI. Real will be upright, so therefore real will be inverted, so it would have a negative HI, and therefore a positive DI. Once again, those make different uses depending if you're talking about a mirror versus lens. If you have a mirror like this is known as a concave. And remember that light would then bend towards the focal point. This is a concave / converging. Verging. Then if I had one that looks like this would be a diverging, where light would actually diverge. This is known as a convex. So those are for mirrors. And then for lenses, just as a quick reminder, we had this one here. And when light travels through, it will converge, but on the other side. So this is converging, or known as a convex lens. And then we also had the diverging, which is a concave, which just looks something like this, where light would travel away. So quick reminder, these two will always be virtual, will always produce virtual, And then for converging, convex lenses, concave mirrors, it depends where the object is placed. If it's on the focal point, we said there's no image. Beyond the focal point, yes, there's a real image. Within the focal point, we're going to say that's also producing a virtual. So it depends for converging mirrors and lenses. All right, next one, polarization. Just know that light can be polarized. It can balance out or take only one component of the light all the way through. So if you want light to pass through, you put two vertically aligned plates, and then only the vertical component would come through. If you have a vertical component blocked off by a horizontal component, you should then be able to block out all light traveling through. Understanding the idea of Young's double slit, that when light comes through two openings, it will diffract and also have interference through them. And we're using these two equations to solve this through. Quick reminder that this one here is for small angles. And this one here is for all angles. And when we say small, we're referring to about sorry about that. All angles, small angles, we said about 10 degrees or smaller. Oops, or smaller. All right, so try those out, and then we're using some more Snell's law and some more applications for this. So knowing the difference between diffraction gratings and triangular prisms in terms of the spectrum. So as a quick reminder, if we have white light and we put it through a diffraction gradient, we'll end up getting a central bright spot, which is like pure white. And then usually what will happen is there'll be a rainbow effect happening above and a rainbow effect happening below. This is just one of these. Like you can imagine that this is all n equals 1. And this is all also n equals 1. So for this, with the central bright spot, sometimes can be a rainbow. But then we have this rainbow above and a rainbow below. So if you remember, we came up with blue bends best, and that's for rough-fraction, or red spreads for diffraction. So in this case here, you'd have the rainbow effect where you'd have red on top, and then Roy, so orange, GBIV, green, blue, indigo violet, sure. Okay, so it looks something like that. And then on the other side, you'd have the opposite effect. You'd have the violet there followed by red all the way to the other side. So I'm not going to color all colors, but I'm just going to quickly summarize the colors for you guys. And then blue. Okay, so it looks something like that. If you compare that to white light coming through a prism, so this is white light. We end up getting a different effect. In this case here, we end up getting this bending effect like this, but in this case, blue bends best. Actually, violet bends even better, and then red would be closest to the original path. Okay, so once again, orange, yellow. Okay, so this is assuming that the original path is here, right? So this would be like Roy G. Biv, where blue bends best. And that is for rough-fraction or refraction. And once again, this is diffraction. And you can use these two terms to hopefully solve out for this next question. That's talking about, hey, is it one prism? Or sorry, is it one rainbow, two rainbows? And you can look at the picture above to figure that out. And that's it for the first video.